point is equal to, remember, it'll be S minus Rn, E1 minus F, right? It's on the other sheet, but if I just look at this, I can see it right there. Again, this picture's invaluable. I always use that picture to work problems like this. Okay, so let's locate the delta point. So S minus Rn is delta. I know I didn't mess that one up, so I'll put that in there first. And that's somewhere, delta's on that line. And hallelujah, I'm on the paper. And liq-liq extraction, sometimes you can, the flow rates that you run out there, you can end up with your graph paper extending across the library. Literal whole library. I mean, it could in principle be the big library. It can be located in infinity. You like that, don't you, Jess?
Yes, I do.
And actually, though, if it's infinity, actually, it doesn't mean you can't work the problem. If the delta point is very, very far away, you can still draw your lines. Let's not get into that right now. Okay. All right, so here's our delta point. So now, so delta is En minus R1, E1 minus F, S minus Rn, E1 minus F, E2 minus R1, E3 minus R2, etc. So notice what we do now. Okay, now how do we find S1? I'm sorry. How do we find R1?
By connecting delta.
No. No. That's operating line. What are the two lines we have in the K-Tilde? Operating lines and equilibrium lines. Same thing here. Okay, so where's my equilibrium line? Basically, I'm going to have to follow a tie line. Okay, so look, you got a fancy solution of the conjugate line. So I'm just going to go on and say I'm going to estimate that R1. Okay, I'm going to estimate that R1 just following parallel to this tie line that's already there. I'm going to estimate that R1 is about right here. All right? Okay? It's an EE. What's an EE? It's an eyeball estimate. Okay, let me just put a dotted line there to show that's what I'm doing. Okay, so that's my equilibrium tie line. Okay, now what do I do? Okay, R1 is on the same line with E2 and delta. All right, again, I'm here. Now we're trying to get, we've got R1, we get E1, equilibrium gives us R1. Now we use operating and the delta point to get E2. So what do? I draw from delta through R1. Delta, R1, and right there I hit. So I guess I better draw this. The delta to delta through R1 and locates E2. And notice there, my E2 is right on an equilibrium line. So now what I do, follow equilibrium line back, right, to R2, which is now right here. Okay? And again, looking at this picture here, notice what we're doing. So we got a delta point, E1 and F, was from our mass balance. Then we did E1 to R1, Then we do the operating line to E2, equilibrium to R2, and now operating to E3, and we just continue this process. Okay, so let's do. So now we've got R2, which is right there at an equilibrium top point. Okay, then you see we're getting a little more separation now. Okay, it's been pretty tight. We haven't got much of a separation. Okay, we're getting a little bit more separation there. Okay, so now we're at E3. Okay, so we continue this process, and we just simply work our way, going back and forth between equilibrium and operating lines until what? Until we get tired? Okay, hopefully before we get tired, we hit what first? Hopefully before we get tired, we hit RN. You think you're going to hit RN right on the money? You might. Depends on how good you are at fudging your line. Just like in McKay-Tilly, though, it doesn't matter. Right? In McKay-Tilly, you get fractional stages. In liquid extraction, you get fractional stages. And so if you go on past RN. Yes?
Sorry, maybe I'm just confused. How do you pick where like your next one is, besides just eyeball estimate and you just picking a point and drawing a line?
How do you do what? So what, for E3?
Yeah.
For like making your,
R3?
I mean, I know like, you know, you pick a point for R and you draw it from the delta over, but how do you pick that point? I mean, you said eyeball estimate, but
Wait, how to pick which point? So right
any
now
of
it's
them.
E3.
Any of them.
R1.
How do I get R3?
Yeah, that works.
Basically, I interpolate between the existing tie lines if I don't hit a tie line right on the money. I mean, we talked about we draw a conjugate line. So, but as I've mentioned to you, I may, you know, in working problems like this, I may just tell you do not bother drawing.
Is it like you do this and then you basically make a conjugate line
So,
and then you go to this
if you
point
look
and
at
you
your
get that point through this and you get your next one like
solution.
that and you get your next point down.
Okay, yeah, I think so.
Okay, that makes sense, thanks.
In fact, so here's the solution to the problem. And you have a handout for this. Okay, so, all right, so let's show how we got, R3. Okay, so here's E1, here's E2, E3 is right here. All right, so as Bradley mentioned, so E3 is basically between these two tie lines here. So there's my E3. So how do I get R3? Okay, if I don't want to mess with conjugate lines, I just have to basically just interpolate between these two tie lines on the other side, Bradley, and just do the best I can. In this case, I have created a conjugate line. So my conjugate line, notice, is right here. And I take that and I go vertically down until I hit the conjugate line, which is right here. And then I go horizontally over. Now I didn't go vertical and horizontal on the equilateral triangle because it was equilateral and I had 60-degree angles in there. But here I've got a right triangle, so I go vertically and I go horizontally. So I go over to here, and then here, good luck, I hit it. Right here is our first.
Wait, do that. So how do you do that one more time? You go straight down. I got that one.
Well, and then I go straight across.
When you go down until where? Until you hit the line that you.
This conjugate line that I drew.
Yeah.
We didn't,
We showed y'all how to create that last time.
can you refresh our memory?
We didn't do it. Like, is it the same process as you did on the?
Exactly. It's just here. It's more. Yeah. I mean, here's the equilibrium data. So basically, these equilibriums. So basically, using these existing tie lines, I went over horizontally from this one and vertically from this one. So to create one.
Okay.
So let's see how we got a point on there. Let's do this one right here. Okay, so that one's right there. So I go over it horizontally. Over there. I drop vertically from there. And that's how I got that point. And then I did that for a whole bunch of them. And y'all have diagrams. So you've got another diagram. You can make a copy so you can go back and do this. So I've already got the conjugate line on there. Okay, and I'll just look at I created. Know what? Well, you can do it with an equilateral. This one is easier because you go just vertically and horizontal. Oh, that's what you mean that you want though. Easier. Okay, anyway, so this is continuing the process that we started, and you notice that we basically stepped off, and E8 is right here, and it ends up down here below Rn at about 6%. So 8 stages, 8 plus stages, well, 8 stages will, and then what do? Notice that you count each one of these. So notice that we counted E1, E2, E7, E8, and then Rn equals R8 will accomplish more than accomplish separation.
So what the hell is this?
Okay. Rn equals 0.08.
Does this mean anything?
We reach
We don't use it. It's just showing faces.
0.06 for Rn acetone. Okay? All right. Any other questions about this? Okay, so let me look at my notes here and just, okay, we haven't calculated flow rate yet.
I've calculated it's about time to go there.
Okay, let's go on, and before we leave, let's go on and calculate. Okay, so notice that we have, so now let's complete our acetone balance. So we have 0.28. So 0.283 times 335.5 XAM times M is equal to E1 XAE times E1 plus XAR times RN. Okay. XAE turns out to be 0.48. Right here. See, that's 48% right there. 48% acetone. Okay. E1 plus XAR. Go on and put your design number even there. Even though we got the 6%, go on and put in. And then it's 335.5 minus E1. This is S plus F equals E1 plus R. And then we solve and we get E1. This one's 70.3. And Rn equals 165.2 kilograms. And notice you can also go back and get the number, the passage stream flow rates. Okay. All right, so that's how you do it. Okay, so next time we will look at this and we'll calculate selectivity and distribution coefficient for one of the pylons. And then we'll start talking about the limitations. Okay, this is the design. We have minimum number of stages, infinite reflux, maximum number of stages, minimum number of stages. So we'll look at those analyses.